Welcome to the first video of this week in which we introduce the notion of an Ito process and of stochastic differential equations. The reading material for this week consists of the same references as last week. So in our textbook by Mikosh we have the third chapter and we have two additional references by Laurie and Carleen, and the exact information you can find on our course webpage on Canvas. We start by a short revision on derivatives and differential equations. So suppose we have a function ft on the interval 0t. Then we say that f is differentiable if the differential quotient consisting of the difference between the function f at point t plus h and the function at point t divided by the difference in the points h exists. The limit f prime is called the derivative of f at t. A differentiable function can be approximated by a linear function. So if the function f is differentiable at point t0, we can approximate it for close by values points t, such that f at t is approximately f at t0 plus this linear function, so coefficient mu t0 times t minus t0. Here the coefficient, so the slope of the approximating linear function, is exactly the derivative. So the derivative describes the slope of the tangent to the line. So the picture would be if we have a nice function, so that is here at that point differentiable, then we can approximate it by this line, where the slope of this line is exactly the derivative of the function. In differential notation we can write this equation, so we have ft minus ft0, so that is dft, and here we have then mu t times dt, so dt is the difference between the points. So that is the same linear approximation described in differential notation, and the fundamental theorem of analysis relates this to the integral. So we have the global change in the function between point t0 and point t being the integral of the first derivative over the interval from t0 to t. Now a common problem in mathematics, in science, is that we sometimes don't know the function itself, but we can relate the change of the function, so the rate of change, to the function itself. So we have for some known function g, depending on two arguments x and t, that the differential dft equals the function g evaluated at f of t and t times dt, or in terms of the first derivative, so the first derivative of the function f equals g of the function and t. Such an equation is called an ordinary differential equation, as it relates the function to its derivatives. As an example, consider the price process of a risk-free investment with fixed interest rate R. Then we can say that the change in the price or in the value equals the interest rate R times the current value times dt, so the time interval over which we consider here the interest earned. That can be also written as the first derivative of the price process being equal to R times the price process. Now if you look at that, we have here that p prime divided by p equals r. Now we know that 1 over x is the first derivative of log x, and we have here p prime, so that looks like an inner derivative in the chain rule. So we can write this part here actually as the first derivative of log pt. And then after integrating, we have that log pt equals rt, so that is now the integral on the right hand side, plus c. Now taking exponential on both sides, we find that pt must be some constant c times e to the rt. So that is the general solution to this differential equation. And with the boundary condition, so for instance the value of our price process at point 0 equals 1, we find that then the constant c must be 1. Now we want to extend this to an environment where we have randomness. So for comparison, we consider now a risky asset with the price process ST, and we assume that the percentage return described as the change in the absolute value of the price process divided by the initial value of the price process, so that is the percentage return, that the expected percentage return is constant and proportional to the time interval taken. Likewise, the variance of the percentage return, which describes the riskiness of the asset, is also constant and proportional only to the time. So it's not time varying. This constant here is constant over time. Additionally, we assume that the changes delta st are independent from the past, and additionally that st has continuous sample paths. With this, we can write the change in the price process as approximately mu times st times delta t, so that is basically this growth according to the mean equation, then plus sigma st, that is here from the coefficient sigma, and divided by that st, times epsilon t, where epsilon is normally distributed with mean 0 and variance delta t. So that is the randomness, the noise coming into the system, and which expresses the riskiness of that asset. The normality here that we have assumed, so that is not really an assumption, that is a consequence of assuming to have continuous sample paths and the independence. So more precisely, if we let delta t, so the length of the intervals between which we consider the process here at discrete points in time, if we let that go to 0, we get by the function central limit theorem, which we met in week 3 actually. We have for the partial sum process that is constructed out of these epsilons here that depend, of course, on the number of time intervals in which we divide our time interval from 0 to t. So that is this index here. So here we have the partial sum process constructed out of this epsilon process, and this converges by the function central limit theorem to a Brownian motion. So this suggests to rewrite this here actually in differential notation as dst equals mu st dt plus sigma st dbt. Or of course we can as well write that first still in discrete time. But of course that is always only approximate, and we want actually to make that precise. So we could write that also in discrete time, and of course we want to find a limiting exact expression for that. However, the problem is that here our Brownian motion that comes in here via the function central limit theorem is not differentiable, so this cannot be an ordinary differential equation that is understood pathwise. In particular, as b is not differentiable, this rate of change, or the first derivative of our stock price process, is also not defined. However, we can take the idea from the fundamental theorem of calculus and describe change over time period in terms of local changes and relate these to global changes. So the local change of our stock price process or price process of the risky asset is again mu st delta t plus sigma st delta bt, and by summing up these we get the global change st minus s0 we add all the changes, and approximately these can be written in this form. Now we make the partition finer, so we let n tend to infinity, and of the intervals that we have, all of them together uniformly tend to 0, so the maximum interval length goes to 0. With that, we see that the first sum converges almost truly to a Riemann integral, so that is exactly a Riemann approximating sum. So in the limit we have the integral of mu s tau d tau. And the second sum converges in mean square to an stochastic integral. So here we have exactly the defining Riemann-Stieltjes approximating sum, which, because we have here Brownian motion and a process that is derived from the Brownian motion and that is adapted to the filtration of the Brownian motion, and therefore has the same continuity properties as the Brownian motion. By that, this Riemann-Stieltjes sum will not converge pathwise, but only in mean square, and the mean square limit is called the stochastic integral, denoted as integral of sigma s tau db tau. So with that together we find actually an integral equation. So the global change in our price process from time 0 to time t can be written as a Riemann integral from 0 to t mu s tau d tau plus a stochastic integral from 0 to t of sigma s tau db tau. Such processes of this form are very important and therefore have been named stochastic processes. So suppose that Bt is a Brownian motion with canonical filtration Ft, and we have two stochastic processes that are adapted to this canonical filtration Ft, so alpha t Bt. Then a process xt that is given by this equation, so xt equals the starting point x0 plus this Riemann integral over the process alpha s, and this stochastic integral over the process beta s times dbs. It is more convenient actually, and the whole finance literature using stochastic calculus is doing so. It's convenient to write such processes in differential notation. So instead of writing xt, etc., we say dxt, so the local change, and of course the change here, the global change here, is the integrated local change. So we have the integral from 0t of dx tau, and by leaving off the integral signs we have the differential notation dxt equals alpha t dt plus beta t dbt. So both equations mean the same, only we leave off the integral notation. So as in all terms we have an integral, it's actually redundant to write that, and we can simpler and more clearly write it in this differential notation. Even so, Mikosh refrains from doing so. It's actually the common standard in the field to write rather differential notation. Even so, it should be clear from what we said that such a differential equation here that we have, or such a stochastic differential, has nothing to do with the common notion of differential, because we don't have derivatives. It should be only understood as a shorthand notation for such an integral equation. So example of such Ito processes could be, for instance, Brown motion with drift. So we have xt equals sigma bt plus mu t. So linear drift with sloped parameter mu. Then the stochastic differential of x, so dxt equals sigma dbt plus mu dt. And of course, integrating here this part, we, as the sum of all the local changes is the global change in the Brown motion, we get back our Brown motion starting at 0, and here the integral of mu over the interval from 0 to t gets this linear slope mu t. Next, if we have the process xt equals a half bt square minus t, so we have seen this martingale before, so in the last set of problems, and also we have seen that actually when deriving our most basic stochastic integral bt dbt, so the stochastic differential of this process here is given as the stochastic integral of bt with respect to dbt. The differential notation, unlike the integral or the global changes of xt, describe the process in terms of local changes, and sometimes these local changes depend on the value of the process itself. So we have seen that already for our price process for risky assets, so usually we think of stock prices, so where the change in the stock price depends on the current level of the stock price. And that is exactly due to the fact that when investing we actually expect a certain percentage return. So if we invest more, of course we we also expect a higher return, but the same percentage return. And the same equation can be written in this form. Next, we have the so-called Waschek model for interest rates. So if RT is our process for the interest rate, then the change in the interest rate equals alpha times gamma minus RT times dt plus noise that does not depend on the current level of the interest rate, so that has constant volatility sigma. So here that means that regardless of where the current price, the current interest rate is, we have the same noise, while this equation here, this part, means that we have a mean reverting process. So for instance, if RT is larger than gamma, then we have here a negative value, and as alpha usually is a positive constant, we have here a negative trend. While on the other hand, if RT is smaller than gamma, then we have a positive value here, and we have a positive upwards movement. So that means that the process is driven back to gamma, which then would be the long time mean of the process. The problem with this model for interest rates is that due to this constant noise that we see here, it can actually lead to negative interest rates, which is unrealistic. Nowadays, not anymore. But in order to avoid that, one can actually introduce here some additional factor, like square root RT, which actually prohibits the process from crossing the zero line. So here the volatility will become smaller as the process closes into zero and keeps the process actually away from zero. So what this shows is that we usually can interpret such local changes very nicely. We can up by fundamental considerations with models described in terms of these local changes, and also that the process of interest, which is described here by the differentials, also appears on the right hand side. So that is no equation that we can simply integrate, if one can speak of simply integrating when dealing with either stochastic integrals, but we cannot just integrate the right hand side in order to get RT. So it is not really helpful here, for instance, to write st equals s0 plus the integral of mu st dt. And then I should write, say, tau 0t plus 0t sigma s tau dB tau. Even so, that of course is correct. These integrals cannot be evaluated because we don't know the process as tau, because we define it by this equation. So that actually is an equation rather than just a defining expression for the stock price process and needs to be solved. So more generally, a stochastic differential equation can be specified in two forms. So for a process x, it would be of the form that we have dxt equals a term mu xt comma t, so it might depend on the current value of the process x, and on time t. And here the stochastic integral part, where the coefficient or the adapted process also depends on the current level of xt and time t. So in the stochastic process form, this here is exactly the mu t, and that is, or alpha t I called it, and that is some sigma t. So this is more specific, where the adaptive process is allowed to depend only on the path of the Brownian motion via the current value of the underlying or of the process of interest xt. And instead of using differential notation, we can also write it in integral notation. So xt equals x0 plus these two, so this Riemann integral and the stochastic integral. And it should be clear that both expressions exactly mean the same. Here we only have left off the integral sign, and additionally would of course need the starting condition. So for instance x0 equals x0, and then we can start here with a specific value x0. So again, our Brownian motion is not differentiable, so the stochastic differential equation is not really a differential equation, but it's actually an integral equation, namely given by this equation putting together Riemann and the stochastic integral. Because the process of interest appears on the left side as well as on the right hand side via these two coefficient processes mu and sigma, it's truly an equation that needs to be solved. So it's an indirect description of the process. The process B, the Brownian motion, is called the driving process of the stochastic differential equation. So it's actually the noise coming into the system and keeping the stochastic system alive. So consider the stochastic differential equation as before. Then we say that the process X is a strong solution of the stochastic differential equation if it is adapted to the Brownian filtration, so the canonical filtration of the Brownian motion of interest. And the integrals associated with the stochastic differential equation are well defined as an Riemann integral and an stochastic integral. So that means we cannot just write down such a stochastic differential equation, but in order to make sense, we have certain conditions on these coefficient processes mu and sigma, because for instance for sigma we need that and then if we take that up to time capital T, then we need that the expectation of sigma xt t square dt actually exists, so it's finite, which would be the variance of this stochastic integral. Lastly, of course, the strong solution should actually be an explicit function on the underlying Brownian sample path as well as on these functions, which of course again so recursively xt again depends on the Brownian motion, so truly of course it is recursively depending on the one Brownian sample path of interest. and such processes are also called diffusions. Like any equation, a stochastic differential equation may not always have solutions or a unique solution. Unique solutions, however, exist if, for example, both coefficient processes mu xdt and sigma xdt are bounded and uniformly Lipschitz continuous in T. So bounded means that if we take these as functions into arguments, x and t, that in absolute value they are bounded by some constant k, same for sigma, and Lipschitz continuity means that, say in the first argument, if we take x1 t minus mu x0 t absolute value, then this can be bounded by some other constant times x1 minus x0, and the same would also be necessary for the time. So if we have, and then of course the same x, but another time s, say, then we have and yet another constant t minus s. So that is Lipschitz continuity. It's slightly weaker than the functions being differentiable. So it allows, for instance, for abrupt changes which are not allowed for differentiable functions. Also, like for ordinary differential equations, solutions are seldomly available in analytically closed form. So that means that if one wants to solve such a stochastic differential equation, one in most cases has to rely on numerical methods. These, however, will not be the topic of this course. Now finally, to close this session, we have seen that Ito integrals are martingales. Now, a very interesting fact in this case is that the converse is also true. So that means every martingale with respect to the Brown infiltration is actually an Ito integral. And this is called the martingale representation theorem. Like we have a martingale representation theorem for the binomial model, we have it here also for the Brownian motion model. So more precisely, if you have a standard Brownian motion P with natural filtration F, and let M be any martingale with respect to this natural filtration of B, such that the variance exists for all times t, then there exists the process phi that is also adapted to the natural filtration of the Brownian motion, so indirectly depends on the Brownian motion up to time t, and additionally satisfies this property here, so which actually makes phi a possible integrand for Ito stochastic integral. Then the martingale M can be written as the starting value of the martingale at time 0 plus an Ito stochastic integral from time 0 to time t of the process phi with respect to the Brownian motion B. The martingale representation theorem is very important to understand what processes are Ito stochastic processes. So, as an example, we consider the process xt being given as the mean square limit of the sum I equals 1 to n for some partition of points ti, where we take the Brown motion at point ti times the increment of the Brown motion over the interval from time ti minus 1 to time ti. And furthermore, we subtract value t from this limit here. Now, on first sight, it might seem as if this process here would not be a stochastic integral, because in contrast to the definition of a stochastic integral, where we require that for an increment we take the integrand at the left endpoint, we have here the right endpoint. So this sum here taken for its own certainly would not be a stochastic integral. However, as has been seen in the tutorials, the mean square limit of this first sum equals bt squared plus t times a half, and together with the minus t that we have here, we then get a half bt squared minus t. Now, this is a martingale, and as the martingale representation theorem says, every martingale with respect to the Brownian motion, filtration of the Brownian motion, is actually a stochastic integral. So it has a representation as a stochastic integral. There exists a measured stochastic process that is measured with respect to the filtration of the Brownian motion as integrand, such that the integral over this integrand times the Brownian with respect to the Brownian motion equals this process here. So, and indeed we can see that if we take again our limiting sum, but now we replace bti by bti minus 1 plus bti minus 1 times now the increment that we already had, minus t, and that again as a mean square limit. We can rewrite this as actually now the mean square limit of the sum with the left endpoint times the increment of the Brownian motion over the interval, plus the term, the sum of the squared increments, and that converges in distribution or in mean square to t. So that minus t converges in mean square to actually 0. So by that, as we only consider mean square limits, this is indeed the stochastic integral from 0 to t of the Brownian motion with respect to the Brownian motion. So indeed it was a little bit deceiving here, taking the right endpoint. The combination of all terms is important. We have to take the mean square limit, and only that is relevant for deciding whether we have a stochastic integral and not. And actually, as every stochastic integral is a martingale and vice versa, it is sufficient to show that a process is the valid martingale and has a stochastic representation, is sufficient to say, okay, we have a stochastic integral. So here we know that it's a valid martingale with a valid variance, and that actually already determines that we have a valid stochastic integral representation. Now, if we want to decide whether a process is a martingale, on the other hand, it is sufficient to show that actually it is a stochastic integral. Now, the question is, how do we do that? And that will be the topic of the next session, the Ito formula that allows us actually for a given process so if we have a process xt that is adapted to the filtration of the Brown motion, then we can decide whether xt is a martingale if we actually can find its stochastic differential, so a representation as a process consisting of a Riemann integral with integrand mu t, where mu t is adapted to the filtration, and a eta stochastic integral with respect to the Brown motion, where sigma t again is adapted with respect to the filtration of the Brown motion. And then this is actually a martingale if and only if the trend term here equals 0, so the Riemann integral equals consistently 0, and we only have the eta stochastic integral. And in addition, of course, we have to make sure that the eta stochastic integral really exists. So if we have such a representation, we also have to check that the integral of the mean of sigma t square dt actually is finite, or alternatively that the variance of xt is finite. So that will be the topic of the next video. Will be provided hopefully within the next 24 hours. Thank you for watching, and bye-bye.